Okay.
Okay, let's get started. Hello, everyone. Welcome to this week's Ground Seminar. Our first speaker is Yinghao Huang from BirenTech in Shanghai. Yinghao is currently an AI researcher at BirenTech with strong background in applied mathematics and research interests in theoretical and computational fluid dynamics. He obtained his PhD in applied math in 2019 from University of Surrey in United Kingdom. His current research focuses on AI for science and improving AI techniques to simulate nonlinear PD systems. Welcome, Yinghao. You may want to start the presentation.
Thank you, Donald. Yeah, thank you for inviting me to give this seminar talk. I'm actually very excited to give this talk, and this is actually the work I did, sort of related to the work I did when I was doing my PhD. Which was concerning the sloshing problem. And this is an interesting problem because it's first, it's a fluid dynamics problem, which I really enjoy. And then second, it's a problem that also involves a free surface, which is quite common in a lot of real life problems, such as the sloshing problem, which I'm going to get to it in a second. Today's seminar talk is going to structure as such. So I'm going to talk a little bit about the background and application of sloshing, so why we want to do this problem. And I'm going to give a little bit of descriptions and a little bit of details of the governing equation that is that's behind of this sloshing phenomenon. And then the some existing theories that we were working on, and then finally we're gonna talk about the physics-informed neural network framework, which I think I believe most of you are quite familiar with. And then I'm gonna talk a bit about this the bif-PINN method that we recently working on, and a little bit details about how this works and an application to the sloshing problem. And then finally, I'm going to talk about sort of the possible the direction of where the AI for science might go, and how is it, what we can borrow from, like, for example, like ChatGPT, like those large language models, and some ideas, and where this could go, basically. So my background, as Zongrong has introduced, is actually mathematics. So I'm quite interested in the theory and sort of the numerical methods of a fluid dynamics problem. So that's my background on it. But then I joined BirenTech back in 2021. Yeah. So, and then we're starting to focusing on an AI models. And one area is actually the AI for science. And then the one sub area in this is actually, which I'm, my favorite is the PINN method. Why is it good? And I'm going to talk a bit more about why this is is very important in this, in the future of sort of a scientific computation. It's some benefit of this PINN framework, which I believe is powerful. And right, so I'm gonna start with a little background and application of the sloshing problem. Oh, by the way, yeah, feel free if anything it's not clear, and then feel free to stop me, and then we can have a discussions about it, which I'm really happy to. So it's been a quite a while to give such a long seminar talk. So yeah. So right. So so what is a sloshing problem? So quite simply put, it's actually something like, for example, water in a partially filled container that's open to, for example, air, right? And then you have this this sort of interaction between the fluid motion that's residing inside the container, and also the motion of the container, or the vessel motion, and they sort of interact with each other. I believe there's a couple of years ago, there's a quite famous paper on how walking with coffee, so how that the human walking, how that interact with a cup of coffee, and then the motion of coffee can stabilize the whole walking process. So that's sort of the kind of the ideas of the sloshing problem, and a few main example of the application of this of sloshing is that one is the tune liquid damper, and this is not often used in like skyscraper or large structures, where it's used in place of a tune mass damper to build resistance against strong winds and earthquake or some other natural disaster through the use of this device, tune liquid damper, with using the fluid velocity and the breaking waves mechanism, also the baffles to sort of reduce the motion of those phenomenon. And also we have the application in transportation. We have this liquid fuel liquid sloshing inside, for example, rocket or airplane or boat, and that the list goes on, and you're studying the stability of this problem, and to help to not having this the stability property of the transportation. And lastly, which I'm going to talk a bit more about, is this wave energy extractor. This is actually the sort of the background of my how where my PhD sort of originated from, and it was actually to do with how to extract this endless energy from ocean. We have this endless waves, and how are we gonna make use of that? How can we extract those wave energy? And that's one quite a good real life application that I thought of. Okay, so here's an early design of this like a wave energy converter. So basically, you have this wave coming into contact with this converter, and so the waves coming in brings in some air, and this air gets trapped, and this builds up pressure, which is gonna kick off some power takeoff systems, such as the air turbine. And this is how you sort of generate the energy from this endless waves. Right. So the problem is that to design such a wave energy converter, you require to run quite expensive CFD computational fluid dynamics simulation. So often to just run a really relatively short simulation requires days, if not weeks, of time to simulate such thing. And if we want to design a good energy converter, we're gonna need to run a lot of experiments, and that simply just too expensive to run. So what happened is that the company at the time went into collaboration with the group, Surrey, which is mostly my supervisors, and they designed some efficient numerical method that was able to simulate the simpler problem, albeit also quite accurate, using the theory of mathematics and some specialized numerical scheme, which I'm gonna talk a little bit about. Okay, so as I mentioned before, the direct 3D CFD simulation is quite slow and expensive. So what can we do to gain a better understanding of the whole problem? So we're gonna start with something very relatively straightforward. We're gonna study the natural frequency. We're gonna study the linear problem of this system. And we're gonna learn the property of all the linear modes, and and then we're going to learn, how this the interaction of the fluid sloshing and also the vessel motion. And then we're going to the next thing we're going to think about is going to be the weakly nonlinear case, where the higher, when the sloshing amplitude increases, you start to get those modes to interact with each other, and that's a pathway to some very, very interesting nonlinear phenomenon, such as the internal resonance, which also I'm going to talk a little bit about. And throughout the path of trying to get try to solve this difficult problem, we started also looking into this Lagrangian fluid dynamics. So where we sort of transform from the standard Eulerian framework to a more rather particle-like Lagrangian framework. And finally, we're gonna talk about a little bit about this shallow water theory, and a little bit about this how we design this simplify the problem to make it into something that's rather easy to work with, and also to observe more interesting fluid phenomenon, such as the vorticity. We're going to have to look into the non-shallow water regime, but there are some difficulties, such as the numerical instability that commonly occurs in those Lagrangian fluid dynamics. And finally, we talk about all those difficulties that we face in this conventional conventional methods. How are we going to use the latest techniques, such as the AI techniques, to solve all this problem? Okay, so right, let's jump on. Right, so the governing equation. So what is this problem really? So now I'm going to describe it a little bit more in details. So we have, so this is an example of the a problem in 2D. So what we have is for example fluid in the container that is, for example, water, and the water is they makes up the interior of this fluid, and we also have this the free surface, which is the interface between the water and the air. And so inside this container, the water is gonna slosh and so on. And also because it's induced force on the wall, so this is gonna induce some motion, and which is the vessel motion. In turn, it's gonna affect the fluid resides inside the container. And we also have often have external forces, such as a spring or pendulum outside, or other some induced wave external forces that there are many type of forces that can also be a source for the forces. And so that's basically it. That's the simple sort of the schematic, if you like, of the whole sloshing problem. So we just want to study how this whole thing, how we can gain a sort of better understanding of the whole problem. How the sloshing is interact with the vessel motion and so on. Okay. So the governing equation in this case is actually it's fairly straightforward. So we have the Euler equation that governs the interior fluid. Okay, so we have the fluid momentum equation for the horizontal fluid velocity and the vertical flow velocity, and we also have the continuity equation, so that sort of ensures that the mass is conserved. And equivalently, you can also derive a Poisson equation for the pressure, as often done in CFD, to relate the velocity to the pressure, because for incompressible flow, the whole system, or the pressure on its own, is kind of meaningless. Okay, it's only the gradient plays a physical role in the whole system. And also as you notice, there's a lack of dynamical turn. So that's the partial T term for the pressure. So there's a lack of the turn that sort of evolves the pressure in time. So oftentimes there's special consideration has to be taken to ensure that the whole system is conserved by using this pressure equation. Actually, but later on we're going to talk about the PIN. Actually, we can use multiple, well, albeit mathematically equivalent equations together to make the neural network to converge faster. So this is something that's been found nowadays especially in the PIN community. And so this is something that's quite interesting, that how so using multiple mathematically equivalent equation can help the convergence of the neural network. So this is something which I found quite interesting. And finally, what makes sloshing an interesting problem and also a challenging one is that you also have to solve the free surface which is part of the solution. Okay, so we make a very simple assumption that the free surface can be represented by a graph, but in reality, sometimes it's not true, right? You can have multi-values and so on. But we're gonna leave it as a future work. So here we're just gonna simplify the problem. We're gonna say it's a graph. Okay. And so we have this kinematic condition, which is where when we track where the free surface is at a given time and space. So this relates. So this equation relates to what a free surface is. Since the Euler equation only tells you the velocity, so this is the sort of the particle, so the free surface position, if you like. So this is something that we need to find as part of the solution. And also we have the very important condition that is in sloshing, that is the dynamic condition. So what this plays, the use of this condition is that it actually drives the whole sloshing process. So without this, the system it just won't move, basically. So this is a very important condition also. Right. So to make the whole thing computationally slightly better, is we can use you can use the Lagrangian frame of reference. So to simply put, it's basically where we remove the fixed coordinate in the Eulerian setting and to something that we are tracking the fluid particles. Okay, so now our coordinate system sort of moving in time. Okay, so this is done through the use of this particle path line formulation, and where we say with the the fixed physical location is transformed into something that's time variant. Okay, and also when we take the time derivative of that x, we're going to get the velocity, right? And to get to that, to sort of to derive the Lagrangian equation from the Eulerian counterpart, there's a multiple ways to do it, but one of the simplest way is just to use the change of coordinate, where we start with the Lagrangian frame and we write down their relationship in terms of the derivatives, and then we're gonna invert this Jacobian matrix, and we get the Eulerian relations with the Lagrangian derivatives. So why do we use this Lagrangian frame of reference? It's basically it's easy to design a numerical scheme that is conserve energy, basically, and this is one of the reasons we do it. And because in sloshing we don't actually care, the fluid state at a specific point. We only really care about the overall contribution of the fluid. So this is one advantage of the Lagrangian fluid dynamics is that even though we simplify, we somehow, well, not really, we somehow simplify the problem for us, for the sloshing problem, and it's just better for it numerically. Okay, and also another very sort of good point of the Lagrangian coordinate is that the free surface is now found as the particles on the free surface. So basically we don't have to solve the kinematic equation here. So there's one equation down for us. So this is good. All right. So now we use the coordinates transformation that from the last slide. We can actually derive an equivalent set of equations. So that's the Euler equations in 2D in the Lagrangian frame of reference. So they actually looks slightly different to the Eulerian counterpart. One thing that we notice is that now we don't have the sort of convective term, the nonlinear convective term, basically. But now the nonlinearity are actually introduced in the pressure terms. So this is something that's quite interesting. And also the continuity equation, we actually want to we have this time invariant Jacobian map A that has to be satisfied through the whole time. So this is now our continuity equation, and we also if we sort of take the time derivative of the equation, we get another set of another equation that is the velocity constraint, which is often used to make the numerical scheme stable. And you can also derive a pressure equation in the Lagrangian coordinate, but in this case, it's much more uglier. So, but it's still quite useful. And lastly, we have the dynamic condition, which is now simply just the label. So we have the free surface pressure that has to be constant. Well, in this case, we make it simple, so this is 0. So on the interface, that is the air, where the air and the fluid meet. Okay. Right. So now we introduce the problem. So what are the existing theories that to describe all this? So first of all, it's quite important as well, is that what I've been talking about the 2D flow problem, but actually the whole the real life problem is in 3D, right? But we found that in most a lot of cases you can actually make the simplification to 2D, because in a lower case the direction that's towards the screen is actually constant throughout that. The motion is constant throughout that direction. So we can just ignore that, and we can just investigate the 2D the 2D problem, which is massively simplifies the whole system. So that's a good thing. And also, to make it even easier, we can actually remove the vertical direction by assuming there's no variation in the vertical direction. So that's the shallow water approximation. So all we are doing now is actually we just need to find out the free surface h and also the velocity on the free surface. And actually, if we do that in Lagrangian frame, it's actually even simpler. Okay, so the whole system in shallow water for the Lagrangian frame reduced down to just a decoupled system. So the h decouples with the velocity. Okay, and now you only have to solve a single equation for the fluid position, and that's just a bidirectional wave equation that's nonlinear. So you can see why from the 3D problem down to the shallow water, we reduce this so much, in terms of the system complexity. But actually, the accuracy, so for the problem we are looking to solve, actually is not too bad. So So this is something that is quite quite remarkable.
Yinghao, can I ask a question?
Yeah, for sure.
Yeah, the 3D looks. How does the 3D look? The decoupled system. You need two velocities, or you still the 3D looks like that, as simple as this.
The 3D problem is just that it's not decoupled in 3D.
I see.
So the 3D just you often have to solve the full problem. Sorry.
Okay. So this is only in 2D. This decoupling is possible only in 2D, right?
Yeah, the decoupling. Well, it's not even in 2D. It's in shallow water approximation.
Or in the shallow, with the shallow water approximation. Yeah.
Yeah. So basically, the H and this G property is actually a high invariant property. So basically, through the use of this, you can impose an initial condition, and that's been substituted into this X equation, and you only have to solve this equation, and then this equation get related back to the free surface. But that's only in the 1D problem.
Okay, got it. Thanks.
Okay, no problem. Any other question? Okay, so. All right, so that's one thing that's interesting while we were working on the sloshing problem. Another thing, as I mentioned before, when we study the linear problem, we have this sloshing. We have this modes that we're studying. Through the finding this natural frequencies of the system. So the natural frequencies, how do we find those? We can through the governing equation we can derive. Making some assumption and the linearize the system, and we can derive this characteristic equation. So for the in the sloshing problem we actually have two type of modes. One is the symmetric mode. So that's the mode that is the sloshing inside the container. It doesn't induce any motion on the wall, so it doesn't induce any sort of vessel motion at all. And on the other hand, we have the anti-symmetric mode. So this, intuitively you can think of it. It actually pushes, on the vessel wall, so that induces motion. Okay, so these two types of modes are quite important, but especially in anti-symmetric mode if you want to keep things moving. And our linear solution actually does the superposition of all these modes, and the exact combination is actually defined. You can find the exact combination through the initial profile of the system, and that's just the linear theory. Okay, what's interesting is that in the nonlinear regime and at the resonance where the characteristic equation for the symmetric modes and the anti-symmetric modes are both zero. That's where things becomes quite interesting. So here, we said that the symmetric mode doesn't induce vector motion, and the anti-symmetric mode does induce motion. So here's what happened: is at the nonlinear regime there are certain parameters settings. So for example, the fluid depth, and then the vessel length, and the density and the spring coefficient, etc. We can find a heteroclinic orbit between these two modes. So what's happening is that it alternates between the symmetric mode and the anti-symmetric mode. So why this is interesting is it's basically makes that it is a pathway for the symmetric modes to induce vessel motion. So something that's we have produced is that we have this vessel motion that's when it's in symmetric mode is produce nothing, but then when it the energy being transferred to the anti-symmetric mode, it starts to induce this large vessel amplitude. So that's no motion. And then it transfers energy back to the symmetric modes, and then back to the anti-symmetric mode. So this is something that is actually very interesting and actually has practical use. And lastly, there's this last theory that I'm going to talk about is the variational principle. So in the Eulerian frame of reference, so that's the Euler equation on Navier-Stokes as well. When we define the Lagrangian, so that's the energy of the system, we use the as been taught in high school, it's the kinetic energy minus the some potential energy, and maybe plus some Lagrangian multiplier as a constraint. So in our case, we have the kinetic energy of the fluid, and also the potential energy from the gravity. Okay, and plus this constraint to ensure the mass continuity. And but actually, if we just use the trick that you learn in high school or in university, then you will find that you can't really do the standard variation on this system. And the reason is that the independent variable x and y, they are not actually they do not belong to the vector space. They actually belong to this what's called diffeomorphism group. So in simpler words, it's a smooth function with a smooth inverse. Okay, so they're a function of some other variables that are in the vector space. So when you actually derive it, you can find the variation principle through the Euler-Poincare principle is actually a function of those arbitrary quantity. So we need to be careful when we deal with things in the Eulerian frame of reference, because u as velocity is a function of x, the position, but the fluid position x is actually also a function of something else. So this is why the whole thing becomes quite tricky in the Eulerian frame of reference when you're trying to derive, for example, an energy conserving numerical scheme. But things gets very easy in the Lagrangian frame of reference, because now you're dealing with the labels, which are in fact in vector space. So here in this case, the whole thing just reduced down to something that can be derived by a first-year student at university, because now the variation of the dependent variable is the position of the fluid. That is arbitrary. So when you do the standard Euler-Lagrange derivation, you will derive the governing equations that we mentioned before. So this is actually quite important if you want to design a straightforward numerical schemes for the long-time integration, and we use those standard symplectic integrators such as the Stormer-Vallée method. So this is something I found quite interesting, and something they're still been working on. This is actually not easy to sort of get into 3D. So this is in 2D is slightly it's much easier in 2D than 3D. Right. So I talked all about this, this theory and numerical schemes in using the conventional techniques. But things get a little bit much easier when we move towards the neural network aspect of neural network area, where everything just works. So I guess this is like a brief sort of explanation of what this how it goes. So the PINN methods, which is in my opinion is very powerful. It's because it's the use of the derivative is you regain in this framework is actually exact. Well, minus the numerical approximation and so on. So the machine accuracy and so on is actually it's quite exact compared to the conventional methods where you have to discretize the domains of the problem. And so during the inference, we we select samples of points, and then we feed it into the neural network, and it outputs our variables of interest. So for example, in the Lagrangian framework frame reference, I input the labels and the time, and it outputs the variables such as the fluid position, the velocity, and the pressure. And for training, this is when things, where PINN is quite powerful, is that it uses the autograd system in the modern day neural network framework, such as the TensorFlow or PyTorch, and it generates this autograd map, which is able to identify what each step is, and then correspond to some backward operations, and it's being recorded. So for PINN, so other than the gradient for the loss function, we also have this gradient coming from the residual of the PDEs. Because of our PDEs, they are actually partial derivative, right? So we can use the same system to produce those partial derivatives, and then we use that to form the loss function. And other than that, we also have to ensure that our system, our neural network, can approximate well on the boundary condition, and such as the dynamic boundary condition I've been talking about, and also the initial states of the fluid. So the final loss will be the combination of these three things. So for example, the governing equation is the Lagrangian Euler system, and then the initial and then we have the boundary condition, that's the solid wall boundary condition, plus the dynamic boundary condition, and then initial condition is the what state I started with for the fluid. And then so for the PINN approximation, how it works is that we use the neural network, such as the the fully connecting network, and use that to approximate U, and then we use the random sample to generate data, and that's how we form the loss. And then, as I talked about before, is the derivative is computed by the autodiff system, and then we're getting this loss term, okay, which is a combination of the three things. And the little caveat is that it's been found that when you try to optimize this loss function, you often run into this problem of the gradients of the loss terms are in different magnitudes. So this can cause numerical issues when you try to optimize them. And oftentimes you enforce like large penalty on those boundary or initial condition terms, or sometimes you can also apply those adaptive penalties against some criterion. So that's sort of often how you deal with this sort of problem, but often it's not ideal, and you sometimes get results that you may not want. You have to do the experiment again, and then you just keep trying for the best result. So that's an issue that bif-PINN is trying to solve. So so first of all, there's to sort of remove those boundary condition and initial condition terms in the loss function. We can use a little clever trick, right? We can use a transformation to make it such that our boundary condition is satisfied by design. Okay, so I like conventional numerical techniques where we're constrained by the form of the equations. In neural network approach, we actually don't don't really care about what the equation looks like. You just feed into the neural network, and then you use a lot, train on a lot of data, and you just get a really good simulation. Okay, so now although we sort of increase the complexity of our equations, but then it's actually the benefit gained from doing this is actually greater than the effort you put in. So for example, here we use this form of transformation to ensure that our boundary condition will be satisfied by design. So maybe an example will be make the whole thing clearer. Is that we use for example, we want to satisfy the condition that u at 0.0 is 1. We can just use the g as 1 and d as x, and then regardless of where your ux is, you're gonna get the u tilde is gonna be satisfying this boundary condition. Okay, so right, so this solves one thing, but what about the initial condition? Okay, so for the initial condition, we're gonna do a similar trick. Okay, we can use a transition function that satisfies certain property, and then we use the fact that the initial condition, well, if it's a valid initial condition, should also satisfy the boundary condition. Okay, because it's something that the user picks, and then we use this transition function that to make the whole transformation becomes something that is both that satisfy both the initial conditions and the boundary conditions. Okay, so why is that? Because at t, when at t is 0, the capital T is 0, so that means at t equals 0 we have this initial condition, so that satisfies the initial condition. As t increases, as t, for example, and t goes to infinity, we can see that this term, the initial condition slowly, gets smaller because this 1 minus t term, this tends to 0, as this tends to 1. So the whole thing, we can see that it converges to the u tilde, which satisfies the boundary condition. But at any given time, this also is true because the u0, the initial condition satisfies the boundary condition. So the whole thing, when you combine the whole things, you get something that is, satisfy both initial conditions and boundary conditions. And some possible choice of this transition function is just the exponential function and the tanh and the reciprocal. So something that can be experimented with. And and we can play as here is an example for that. So for example, when we have a solid wall boundary condition that x has to satisfy a has to be 0 and a equals L, it has to be L. We can use this, you can come up with some expression, and this will satisfy the boundary condition. And then we chose a t, which is reciprocal transition function, and then this will satisfy the fact that solid wall boundary condition and also the initial fluid position initial conditions. Okay. So when you do this, it doesn't matter what x is, this whole thing will satisfy the the boundary and initial conditions. And so in summary, when we compare this whole thing, so in PINN we have to optimize these 3 terms, but in the bif-PINN framework now you only have to solve for the one PDE residual term, and where both boundary condition and initial condition is encoded in this u hat variable. And then we just use the some trick like optimizer, such as Adam or LBFGSB, or a combination of them to optimize this loss function. And it's actually much faster, believe it or not. Maybe except for the initial building the graph step if you're using TensorFlow. And other than that, it's actually optimized faster and converge faster through where we found it. And this this brings other why to do this in the first place. It's actually because the for sloshing it's actually very important to for the dynamic condition. So that's the condition on the free surface to be satisfied to produce accurate results. Because one difficulty is that this boundary condition is rather than on their fixed location. This boundary condition is on a sort of time-dependent boundary. So that's sometimes can be quite challenging to satisfy. But using this bif-PINN method, there's no problem. This is satisfied automatically. So in this, we'll talk about the benchmarks I did for this sloshing experiment using the PINN and bif-PINN. And the first one is the small amplitude sloshing, which is oftentimes when you try to check a numerical scheme, you want to try to validate it against the linear solution. And this is actually quite this is the first step in the conventional numerical scheme, but it's actually for neural network is actually quite challenging, because it's neural network is able to produce a highly nonlinear approximation of anything, but then on a small scale, sometimes it can fail. So this is actually quite a challenging case for both PINN and bif-PINN to get it right. And then we have the moderate amplitude sloshing, so where we increase the amplitude of the sloshing of the initial profile, so that we can see the solution should start to deviate from the linear solution, but also it should also still be similar to the linear solution. And thirdly, we have the Taylor-Green vortices. This is also a standard benchmark cases where this exact solution is known, so we can use that to further validate against our method. And finally, we have a slightly more challenging case, Dunbury problem, where it's very it tests against the numerical scheme, because it introduces rebound motion where when the fluid is hitting the solid wall, and then we should expect this rebound motion. Right, so for the bif-PINN formulation for the sloshing, we can, I won't go to too much detail, but you can see that we just want trying to make the boundary condition satisfied, so such that the solid wall is satisfied, and also the dynamic condition satisfied. And then we use the reciprocal function for the initial condition part to make the whole thing, variables that we're using satisfy the boundary and initial conditions. Okay, so for the small amplitude sloshing, the assumption we're making is that the whole thing is irrotational, so we can use what's called a velocity potential, so to derive a linear solution for that. And then we use the Bernoulli principle to relate the velocity potential to the pressure, and we can get the whole linear solution together. And then to get the particle position, we just integrate the velocities, and we make, because of the sloshing, the amplitude is small, you can just make the assumption that x equals a in those sine and cos terms, and overall you're getting this whole linear solution that's very accurate when your amplitude is small. Okay, so in this case we can see that for both the PINN and the bif-PINN methods in a macroscopic scale, they are actually both did quite well. They're predicting the whole fluid motion quite well throughout time. However, upon closer look.
Sorry to interrupt.
Yeah.
Do you mind going back to the previous slide?
Yep.
Can you speak a little bit more toward this series expansion of the position?
Okay.
So where did the coefficients come? These coefficients come from your they're known a priori.
So basically, yeah. Oh, well, these you can derive it from first principle. So first you make the assumption of that this u is d phi dx and v is d phi dy, and then you just go through the Euler equations, and then you obtain the nonlinear velocity potential equations, and then through that you make the linearization, and then you just say phi equals some epsilon phi star, and then you cancel out those nonlinear terms, and then you can through the use of Fourier series you can get this phi.
But this expansion is done a priori. You're imposing this velocity potential. Is that right? When do you calculate the CNs?
the Cn is dependent on your initial condition. You don't know yet, but it is amplitude, basically amplitude.
Sure. So you're saying as a pre-processing,
So
you would
basically,
expand the
you
initial
know,
condition.
so basically, this is the Fourier coefficient I've written down, explicitly. But then the Cn is something that we don't know yet, because this is depending on your initial condition. Okay, so I just basically, this is amplitude. I just set it to be something that I like. If I want to be in a small amplitude regime, I just set it to be very small. Cn is basically a free parameter in the linear case.
Okay, thank you.
No problem. Okay, so I didn't write it down here, but then the Cn in this case will be something like 0.5, something like that. So very small. So in this case, we don't see any, sloshing on this, macroscopic scale. But then we'll see this in this on the free surface. Okay, this actually is quite subtle. The linear solution is the red dots, but we can't see it here because it's on top of them. And we see that the bif-PINN is able to capture these this sort of linear solution, and as I mentioned before, it's difficult to do for the numerical approach to capture this. So as we can see from the PINN here, it didn't really get it right. Okay, in this scale, and mind you, if you look at the scale here, it's actually 10 to the power minus 5 plus 1. So here, so this is on the very scale where you can see there's a difference in this in the sloshing. So the arrows indicate the velocity, by the way. So we can see that they are actually very, very similar, close to similar with the linear solution. So that sort of indicates that it's quite accurate. And we also did some numerical experiment where we get a list of the values down. But here I won't be showing here, but on the paper the results are there. And then we increase the amplitude. So the Cn now is I think I can't remember the exact value, maybe 0.2. And then we can start to see the whole sloshing process in the macro scale. And by the way, this is the first symmetric sloshing mode. And the reason I pick it is because the neural network doesn't know the symmetric property of the solution. Okay, so we can see that in the bif-PINN. So because I picked the linear solution to be the initial state, so we can see that the initially at t equals 0, it should be the same as the linear solution. Okay, and because the bif-PINN satisfies the initial condition, so now so initially it will be the same as the linear solution, and at earlier time it might still be similar phase with the linear solution, but then later on it will start to sort of having more of those nonlinear effects. So the phase will be it gets more different as time increases. And then the second case where we want to test, well, the third case actually is the Taylor-Green vortices. In this case, we know the exact solution because now we are using this assumption of the mass continuity is satisfied. Well, and we can use the string function, and the string function, they're actually quite interesting on its own as well. So so actually, so that we can decompose the velocity into the irrotational part and the divergence free part. So the string function is actually orthogonal to the velocity potential and is corresponding to the divergence free part. Okay. For our problem, because the Euler equation requires the continuity equation, which is the divergence free, so it's actually using this representation, the mass continuity equation is satisfied automatically. Okay, and then we can actually derive an exact solution. Okay, so C here is actually similar to the Cn as before, which is the amplitude, and then this string function actually describe a set of string lines basically at different constant values. And what these string lines are basically the path of the fluid particles. Okay, and then here the alpha n and beta n, they are actually the sort of the hyperparameters, well, that controls the not hyperparameters, sorry, parameters that control the granularity of the vortices. So here, if we set n equals to m is 1, we have 2 vortices, and they're sort of rotating in the opposite direction. And through this string function, we can derive, using the relationship with the velocity, we can derive the velocities, and then the pressure through the Euler equation. And once we found those, we can just integrate this. We can just find the fluid particles by integrating the velocities. Okay, even though here we're using the this sort of Taylor expansion to integrate the velocities, but let's note that the u and du dt, those are exact solutions. Okay, so the actual error here is actually very, very small, because the velocity and the accelerations are known exactly. Okay, so we can actually derive a sort of very good approximation of the exact solution in the Lagrangian frame of reference, and we can compare those, and we can see that in this case actually, even though there's some some a little non-symmetricness in the PINN method, but actually they're all able to both bif-PINN and PINN are able to correctly predicting this this rotating particles of fluid particles, going in an anti-clockwise, sort of in opposite directions. In this case, it's easier for PINN because it's actually now we're not actually having a free surface, so actually it's kind of easier. but don't get me wrong, it's actually quite challenging in a conventional numerical scheme, because the grids, if you're using, let's say, finite difference method, the grids gets very highly distorted. But using the neural network approach, you can actually, you can use, for example, transfer learning to make it even rotating even further, and it won't cause an issue. Okay. Whereas in the conventional method, you have to remesh and do a lot of things. Yeah.
So I can ask a question about that last comment that you made. So in a Lagrangian method, there are lots of point Lagrangian methods. You run into this issue for this problem because, as you can see, you get clustering at the points at the corners of your box, right? And you can see it. So it looks like clustering along a string. So you either get bunches of collocation points or voids that form. So the point's well taken that a neural network, right, the approximation is insensitive to that. But do you run into an issue where the solution degrades as the collocation points are no longer uniformly distributed and they're bunched up and things like that? Is that what you meant when you said transfer learning, that you would have to
well, yeah, transfer learning is when we when it gets really distorted, because you keep rotating, right? So the graphs gets rotated even further. But then when I try to be honest, I haven't tried it using one single PINN method, PINN session. I just use the I transfer the weights when I tried it out. But then to answer your question, I haven't tried it. I could try that, but at the time I didn't have the resource to make my neural network bigger, or to make my my training points more training points to do this longer time integration. But it's very it could be interesting to try out and to see how it goes. But,
okay, thank you.
no problem. Okay, so that's one third case. So the last case, so it's the dumb break problem, where we can actually find find some exact solution, albeit it's not it might not accurately represent what's really in real world might happen, because in this time we're using the shallow water assumption, and then from this we can use some sound wave velocity sort of concept from the compressible fluid theory. You can think of it as the height as some sort of density, and then you can make this into some sort of shock wave equation, for example, like hydraulic jump and so on. And then you can solve this Riemann problem, which emits this rare fraction wave solution, discontinuous, and they are valid until this the dam break sloshing impacting the wall. And so in this case, we can see that the PINN methods just couldn't quite get it right. The physical the quality of the dam break right. Whereas the bif-PINN method, because it is exact, it satisfies the initial condition and the boundary condition exactly. Well, minus the machine errors and other approximation error. You can actually see it. It's actually it's set to be exactly what I said it to be, which is half the half of the domain, and then we release this sort of sluice gate, and then you can see that this fluid is coming to the right, and then it impacts and then rebounds. Okay, so this is sort of the qualitatively correct behavior we're looking at. But although I do want to make a point here, is that we're making the assumption that the free surface is a graph. So here there's no overturning waves. So this is something that might not be in the actual experiment where it might not accurately reflect on that. So this is something that also is left as a future work to work on. And so in summary, okay. So at the time I only have a very basic GPU. So I only did a very sort of simple neural network, if you like of a fully connecting network. So the sizes are very small, even though the domain they are trying to solve is actually not small in the conventional method standards. So and then the biggest computation comes from the number of training samples. So often, because I'm using the LBF-GSB optimizer, so which is traditionally used for the whole batching, the full batch training. So I'm just using the full batch as the one step. And so for the PINN method, we also have to use some training, some samples on the boundary and the initial condition. Whereas in the bif-PINN case, we just don't have to. We just use the residual on the interior, and that's fine. So overall, in all these problems, we can see that the memory usage for the PINN is actually higher, and the training time per epoch is also greater than the bif-PINN counterparts. Okay, so and here I'm using the DeepXDE by Lulu framework. So with a TensorFlow 1 backend. So in other framework backend like PyTorch, it might be different because how the graphs computed in terms of when they build a neural network. And so to summarize the whole thing, compared to like direct CFD, using this the PINN methods, we're actually getting a lot much faster simulation, both for training and especially for inference. Okay, once it's trained, inference is almost instant. And especially now the AI accelerator like GPUs gets more and more powerful. The neural network approaches can just use those those increasing power of the hardware to get this solution out even faster. Okay, and compared to like specialized numerical methods like those that I mentioned before, and the PINN method actually quite good at dealing with nonlinearity in the equation. Actually, it doesn't matter how nonlinear the equations are. The neural network will be able to capture those nonlinearity as opposed to those standard specialized numerical methods. And this is through my my own experience as well. So this is something that I think is quite remarkable. And one thing that I think is strong about PINN is the use of this auto diff system, which that you're getting this almost exact derivative, which is very helpful in getting those solution right. So finally, so the thoughts on this AI for science area, which I believe is basically, it could be a very strong future for the AI community. So my thought is that so now ChatGPT, for example, those large language models, they are getting more and more powerful, but in its principle, it's still language models. Okay, it's been trained on human data, and human data, us human, we make errors. Okay, but whereas in the AI for science, for example, PINN, we actually using actual data, and those data, and through this loss function in PINN, we're getting the exact numerical feedback. Okay, so this is something that when we want to, in the future of AI, where we want to getting accurate prediction of, for example, fluid problem like weather prediction or some other quite difficult scientific area. This is where I believe AI for science will shine on. And but before we get into that, we actually few things that I think we still need to improve on this PINN method. One thing I think has been pointed out by a lot of authors is that this extrapolation of PINN. Okay, so for PINN, it is often it's often quite bad at generalize beyond its training distribution. This is well known. Although even though it's oftentimes it's not that big of a deal, because we actually just want to have the simulation within our training distribution. But this is just a just something that if we want to improve on the AI, that's to make a better prediction in the future. It's something that we should be thinking of. And one thing is the emergence of those operator learning method, which is actually quite useful in some area. So they generalize quite well, for those, for example, unknown initial states, and you sort of iterate, and you're getting a really good states evolution. But how to combine those two, the PINN and the operator learning, is actually something that I think is also quite useful. I think some existing work, not all comprehensive, but like, for example, there's a PINNO where you introduce those samples in the operators, and you're getting this. You use PINN the auto diff to getting those some physics in the loss. So something similar to that. Another thing is that the PINN method is that you are actually feeding single samples at a time at its basics, right? Then you're not relating the points together. So we need to to have a sort of our AI for science model architecture that similar to, for example, transformers in the attention mechanism, that we can relate points together. I think this is something also. It might be it's been something someone's been working on as well, but I'm not sure. But I think this is something that we also should be looking at. And another thing is the pre-trained model in AI for science. So now the pre-trained model is is ubiquitous in language models nowadays, because the success of ChatGPT. Actually, well before that, there's been many of those foundation models for language model, and I think there's also an area where this could be for AI for science as well. This can also improve those training out of distribution problem that I just said earlier on. And lastly, there's this reinforcement learning method, which I think is also one of the, if not the biggest method that will improve on this AI for science method, because like when alpha goes zero, if any of you guys are interested in the goal, they how these agents with playing against games against each other, and how they there's without human interference, and how they getting those performance that's human can't interfere, and it just blows our our mind. Okay, so and then I've been thinking about this reinforcement learning. This can also be something we can use to improve on the AI for science model. And recently the ChatGPT was also used this similar idea, right? They use the reward model to as an environment to make the whole text generation gets better. So this is also through the use of reinforcement learning. And then I think that the difficulty now is how do you define those action and environment, and how you combine all these. And this will be also something that will be quite powerful in the future. And yeah, so I think my talk is the end. Yeah. So thank you everyone for joining to this talk, and I'll answer the questions.
Yeah, thank you, Yinghao, for your presentation. Are there any questions from our audience?
Hi, Yinghao. This is
Hi.
hi, Yinghao. Excuse me. This is Zhen from the Crunch Group, and I have two questions. So first of all, thanks for the very nice talk. And so my first question is regarding the first part of your talk. You talk about symplectic integrators and conservation of energy. So I'm curious about how they reflected in the second part, because you talk about PINN, but I didn't see like how the energy is conserved for your method or PINN. And the second question is regarding the discontinuity in the Denbrick problem, because we know like neural networks can approximate any like continuous function, but for discontinuous function, can you give some hint on how you train it, or is there any specific trick that you use? That's all.
Okay, so for the first question, it's this variation principle, the symplectic integrator. Yeah, so I think so it was when I first starting to work on this area back in 2021. It had been worked on how to impose these various variational principle in this AI for science framework, but I don't think there were many in this in terms of in the PINN framework. And in this case here, I've just introduced some something that I've been working on, but frankly, I really want to encode this simplicity in the PINN framework, but so far I've not tried it, and this might be something that could be could be studied in the future. And I think that the difficult part is that, as I said in the last point of my presentation, is you have to relate points together, and this simplicity is something that you want to conserve energy, but then it's difficult because you are actually you want to integrate points. And one thing I could think of is the nerf method. The I don't know if you're familiar with it. It's the nerf which you try to integrate light rates, and then you sort of build on this 3D model using neural network. So that's one direction that I think could be used to impose this sort of simplicity in the PINN framework. But it's an interesting direction. And to answer your second question about this discontinuity, actually, I didn't really investigate that deep in that area, but it seems like the neural network itself is very good at dealing with this. And one thing actually, I think the previous audience has asked as well, in the Taylor-Green example as well, there actually are discontinuity in the solution when you if you just go to that slide, when you rotate this the points. If you look at it, because if you just examine the like for a set of point, you will see that in this label space, you actually stretching, it gets very distorted. This line, for example, here when we have this line of labels, and then later time it gets really distorted, and in a single session it might not be okay in this formulation. But then, if the reason I remember now, I did the transfer learning is that because in the next when you transfer the weight, it actually, this is not a problem anymore. It gets rectified. It's on its own, through the neural networks itself and in its weight update. So it's actually something that's, I think, is very worth looking into, and something that is at the moment I'm not sure of. I don't think I'm sorry, I just don't have the full answer for you, but this is some of the advice I think I can give.
Yeah, thanks. That's very helpful.
Thank you.
Yeah. All right. So because of time limitation, we have to move to our second talk. And thank you, Yinghao, for your presentation. And George, do you want to add any comments?
Pardon?
No?
Sorry, is this
No, I'm talking to George. Yeah.
No,
okay.
thank you very much. I was wondering if Mario, but I'm not sure if he's following, because we had a few weeks ago the theory of function connections, TFC, that Daniele Mortari presented a whole theory of how to decompose, how to turn a constraint approximation into an unconstrained approximation. So we have a YouTube channel that lists these talks, and you will see that what you were doing with the initial conditions and the boundary conditions falls under that category. But actually, his is a whole. He has a whole book on that. But one of my postdocs here is worked on that. That was his PhD, combining PINNs and TFC, which addresses these issues that you were talking about, but in a more general context. So these are issues have been dealt with in different contexts. Of course, the free surface is extra difficult because of the Lagrangian formulation, but I think the two are related. So.
All right. Thank you, Yinghao. And yeah, so let's move to our second talk. Our second speaker is Professor Ching-Yao Lai from Princeton University. Professor Lai is an assistant professor in the Department of Geosciences and program in atmospheric and oceanic sciences. Before joining Princeton, she completed her postdoctoral research in geophysics at Lamont Earth Observatory at Columbia University, where she received the Lamont postdoctoral fellowship. And before that, she obtained her PhD in mechanical and aerospace engineering from Princeton in 2018. Her current research focuses on integrating mathematical models and machine learning models to tackle problems in climate sciences and fundamental fluid dynamics. Welcome, Professor Lai. And yeah, we can see your screen. You can.
Okay. All right. Can you hear me okay?
Yes.
All right. So thank you very much for the invitation. I will try to finish in 40 minutes because I actually have to go by 2 p.m.
Oh.
But yeah, I'm very excited to give a talk, especially in this seminar series, because a large part of my recent work is deeply inspired by the work developed in Professor Kanadaki's group. And today so I'm a fluid dynamicist by training, and today I will talk about the group that I've been working on, the work I've been working on in the past 2 years, using physics-informed neural network to solve challenging problems in fluid mechanics and climate science. Okay, so today I'll talk about two applications of physics-informed neural network. The first one relates to solution discovery in the realm of mathematical fluid dynamics. And the second one relates to inverse problem in the world of geophysics. So I want to give you some context about how these two problems are connected. About 2 years ago, my postdoc Yangji and myself are interested in using this technique to combine with the data we have to understand glacial dynamics. At the same time, Tristan Buckmaster was a professor in the math department, and he learned about our approach and suggests that we can use this method to find self-similar solutions in fluid dynamics, which is another problem I'm very interested in. So since then, we, Yangji, Tristan, Javi, and myself have been working together using PINN to find self-similar solutions. And it turns out it works extremely well. So today I'll first talk about the mathematical fluid application, and then I'll move on to the data-driven inverse problem in geophysics. Okay, so broadly, I'm interested in problems that that can be described by the Navier-Stokes equation. And it can be applied to a wide range of problems. So it can be used to describe a dynamics of a bursting bubble that occurs at a scale of millimeter. It can also be used to describe the dynamics of ice sheet, which spans over thousands of kilometers. And one of the outstanding open questions about the Navier-Stokes equation relates to the Euler's equation. So the Euler's equation is the limit where we ignore the viscosity. So here we have a ideal fluids without the viscosity term. And the open question we're interested in is whether there exists initially smooth finite energy initial condition that can eventually lead to a solution that will blow up in finite time. So when we say blowing up in finite time, what we mean is some parameters that, some variables that evolve with time and increase towards infinity at a finite time. So mathematically, the simplest form of finite time blow up or finite time singularity takes the form of a power loss. For example, here, if the lambda is positive, then this expression blow up to infinity when the time approaches T0. And I think for the interest of time, I will skip this slide, but I want to quickly mention that actually in daily life, there are many systems exhibiting finite time singularity. So one of the example is the dynamics of bursting bubble. And one of the very powerful way to describe this kind of finite time singularity is through a self-similar NSOC. So what it means is this year we have the numerical solution of the air-water interface that evolve as a function of time. And it looks pretty complicated, but if you use self-similar NSOC, you can collapse the time and spatial dynamics into some universal profile. So what's important here is that we have the self-similar exponent 2/3, and this describes how quickly the dynamics approach the time of singularity. So here we can, by using this exponent 2/3, we can collapse the time-dependent solution onto the universal profile in the self-similar coordinate. Okay, so the problem is for the Euler's problem, we actually do not know the self-similar exponent. So that's a parameter that we want to find out. And at the same time, we know that if you run a time-dependent computational fluid dynamics simulation very close to the time of a blow up, the requirement for time step is really high. We need to have very fine time step to resolve the singularity, the structure near the singularity. So this poses a computational challenge. And here, we explore the potential to use physics-informed neural network to help find the self-similar blow-up solution. And I hope today I can convince you that this is one of the best methods that can be used to solve this kind of problem. Also, in the interest of time, I will just skip this slide because I think you're all very familiar with the idea of PINNs. Basically, what we do is that we are going to use this as a to directly solve the partial differential equation that's given. And the data loss will just be used to impose some of the boundary conditions and constraints that we know, and we will involve all the equations into the equation residue. Okay, so how do we use PINNs to find finite time blowout solutions? Here I want to provide some of the benchmark examples. So let's start with the de Grigoriev equation. Here we have the original partial differential equation. And then we're going to impose the self-similar NSOC to reduce the PDE into a ordinary differential equation. So this is the final ordinary differential equation we are going to solve. And what's special here is that we have a self-similar exponent, the lambda. Again, this exponent describes how rapidly the solution collapses into the singularity. So here, lambda is a free parameter. And the goal for the PINN here is, first, we want to find a solution profile. So here we have the velocity and vorticity profiles. And second, we want to find the self-similar exponent, which is a free parameter to be determined. Okay, so here, there are a few things we need to do. We define the input and output parameters. We prescribe the equations to be solved. We have some boundary conditions. This is when after the solution converge, after the training of the neural network finish, we have a solution that agrees very well with the non-exact solution. And we can do this for a range of different A parameters in the equation. So here now the solution, we don't have any existing exact solutions, but the PINN solutions, we found a family of PINN solutions for different values of A's. And we can look at this predicted lambda, the self-similar exponent, as a function of different A values. And this trend agrees very well with existing numerical results. Okay, so now let's move forward to the second benchmark example, the Burger's equation. Again, we apply the self-similar NSOC. And now the goal for the PINN is to find the solution profile and the self-similar exponent lambda. Okay, so the first thing we did is to, for Burger's equation there, the solution landscape is quite complicated. So the first thing we did is to fix one lambda value. And for this lambda value, the PINN solution agrees well with the exact solution. However, at this lambda value, we know that the solution is actually non-smooth. So we have if you take the third order derivative of the solution itself, you have a cusp near the origin. And this is revealed also in the equation residue. So if you look at the higher order derivative of the equation residue, we actually have large equation residue near the center compared to the far field. And this is not that surprising, and it's actually helpful to see this because neural network is constructed with smooth functions. So it's not it's expected that the neural network will struggle to capture non-smoothness that exists in the solution, and that's reflected in this magnitude difference. So what we can do, because we're interested in finding smooth solutions, we can penalize the third order derivatives of the equation residue near the origin. So we add this additional term that we call the smoothness constraint into the cost function. And now we also make lambda a free parameter. And after making these modifications, the neural network finds that lambda should be 0.49995, and it's very close to the theoretical self-similar exponent. And this is good news. So we can extend this, we can use smoothness constraint to find even higher order smooth solutions. So here for the second smooth solution, we have to penalize the fifth order derivatives of the equation residue. And then when we add this additional smoothness constraint, we find the PINN can predict that the lambda is close to 0.25, and that's agrees very well with the non-exact value. So I guess I agree with the previous speaker that in this particular application, the ability to use automatic differentiation and to calculate the derivatives exactly is very desirable because here we need to we need to penalize higher order derivatives to find the solution, the smooth solution that we want, and to rule out all the non-smooth solutions. So now we are going to apply what we have learned to the problem of the Euler's equation. Okay, so this is the Euler's three-dimensional Euler's equation. And we're going to make a lot of simplifications. So now we're going to consider the Yinghao scenario, and it's in the axisymmetric framework. So this diagram shows the vertical component of the flow velocity. So you have some flow that goes downward, some flow that goes upwards, and the location where it meets is the place where blowout can occur. Okay, so now we impose the self-similar NSOC. And although the equation now looks more complicated, but is really similar to what we were doing before. So now we have a set of 5 different equations. And in the limit when lambda is larger than -1, we know that the incompressible axisymmetric Euler's equation can be written in these 5 equations. And this also is called the Boussinesq equation. Okay. So for the PINN, now we try to solve these 5 equations. In addition, we have knowledge about the symmetry of the solutions, and we have the boundary conditions. So the goal for the PINN is now to find the solution profiles of 5 different variables, and we want to find a self-similar exponent. Okay, and again, so now this is the PINN framework. Here the lambda is just one more 3 parameters that will be trained along with the weight and biases throughout the optimization process. Okay, so if we just solve this problem without much thinking, most likely you will get some failure result. So this is one of the nonsense result that we got when we first tried the problem. So here again, we fixed some lambda value to just see how the PINN does. And the neural network converts very well here. The equation residues are all of order magnitude smaller compared to the solution itself. However, if we look at the solution profiles, so here we have the velocity and the temperature vorticity profiles, it doesn't really make sense. So we know that the velocity, the gradient of these variables should converge to, should decay far away from the origin. So we need to impose additional constraints that the gradient of these variables vanishes far away from the origin. And this is a numerical framework, right? So we have to define what we mean by far away from the origin. Theoretically, we want we want the domain to be infinitely large. So what we did is to change the coordinate. Here we use the sinh coordinate, so we convert the coordinate from an infinite domain, from a close to infinite domain into a finite domain through the sinh transformation. And what we did is we then rewrite all the equations in terms of the new coordinate system. So when we train a neural network, we are actually in the coordinate system in a z coordinate, and then we're solving the problem within z equal to -30 to 30. But in the actual problem, we are solving in the domain that corresponds to 10 to the 12 away from the origin. And another thing that's important is the choice of the collocation point. So here we put most of the collocation point near the origin because we find that that's important to find the right solution. And we choose the conventional choice of optimizer. So we first use Allen to avoid local minimum, and then use LBFGS to achieve fast convergence. And so last time I gave this talk in Brown, George mentioned that we can also try this self-adaptive PINN to see to learn the optimal weight for the problem. And we actually tried this SIP method as well, and then it's very useful. So it's basically tell us the same thing. So the weight of the collocation point near the origin is more important. So we did it in an ad hoc manner, but this can actually be done automatically with the SIP framework. Okay, so now with all these modifications, now we try a different lambda value. So here we have the fixed lambda equal to 3, and now we have a pretty good solution profile for this lambda value. And we look at the equation residues. So they are 4 orders of magnitude smaller than the solution itself. However, we know that at this lambda value, the solution is likely non-smooth. And this is also revealed again in the large equation residue that we see near the origin. So because we are interested in finding the smooth solution, what we do is, again, we penalize the gradient of the equation residue near the origin. And we make lambda of free parameters to be found so that we can have the lambda that's corresponding to the smooth solution that we want. And after making these modifications, the neural network, the PINN, now can find a smooth self-similar approximate smooth solution. And here we are, our equation residue now are not only small, but is uniformly distributed throughout the domain. And the inferred self-similar exponent is about 1.9. So this is consistent with the suggested value in the literature. And we know that if the previous work relies on computational fluid dynamics simulation, and it takes about a few months to just run a simulation that's accurate enough to show a solution that looks close to a blowout solution. But here we run the PINN framework on GPU, and then it takes about only 10 hours of computation. Okay, so some good news about this work is after our work, there's a Chen and Hao published a preprint that take this approximate solution and then did some additional computer-assisted proof, and then they claim in the paper that this singularity likely exists near this approximate self-similar solution. Okay, so what I'm very, very excited about this framework is that this can also be used to find unstable blowout solutions. So this is the CCF equation, and here the blue and the red solutions correspond to the stable and unstable solutions correspondingly. And for both stable and unstable blowout solution, the equation residue are about 10 to the 9 orders of magnitude smaller than the order magnitude of the solution itself. So this is very exciting because unstable solutions are generally extremely difficult to find with traditional time-evolving simulations. And here, this is the first time a unstable blowout solution is found numerically in the literature. Okay, so if you're interested in learning more about this work, the work is still under review, and the preprint is online. And there's this wonderful quantum magazine that really did a good job summarizing the goal of this project and the history of the blowout problem. So in this article, they quote Charles Fefferman's sentence. So Charles Fefferman wrote the original statement for the existence and smoothness of the Navier-Stokes equation. And he mentioned in this article that our PINN solution is quantitative, precise, and has a much better chance of being made rigorous. Okay. So the summary for the first part of the story, we use PINN to search for an approximate solution for approximate self-similar finite time blowout solution to the incompressible symmetric three-dimensional Euler's equation with boundary. And this is, to our knowledge, the first application of PINN for discovering blowout solutions. And now we are working on using this framework to find unstable solutions. As I mentioned earlier, unstable solutions are generally really difficult to find with traditional methods. And now we are working on using this framework to solve for the Euler's equation without the boundary, which is likely to be unstable. And at the same time, my colleagues in their hobby, Tristan and Gonzalo, they're trying to work on they're trying to take the PINN solution that we found and construct a computer-assisted proof. Okay, so So far, I've been talking about solution discovery. So this is the where we already know the equations and we are trying to find the solutions. Now I'll move towards to the domain of climate science and geophysics, where we do not know all the equations. So the idea is to take the data and then combine with PINN and to learn something new about the dynamics. Okay, so sea level rise is one of the most serious implications of the ongoing climate change. And here, this is the flow dynamics of Antarctic ice sheet. So the flow is driven by gravity, and this continuous flow from inland towards the ocean drives the melting of ice, and that's what contributes to the rising sea levels. So in order to understand, to predict this process, we have to consider conservation of mass, conservation of momentum, and we also have to prescribe the ice rheology, which dictate how the stress respond to the strain rate. Okay, so we come back to the Navier-Stokes equation. When we think about the dynamics of ice sheet, we can take the observation of velocity that's observed from space. And if you plug in the velocity and length scale, you will see that the Reynolds number is about 10 to the minus 12. So the inertia is completely negligible. Therefore, here we focus on the Stokes equation. So this is the opposite from the Euler's equation. And there are some desirable nice properties about ice sheet. So the horizontal length scale is much larger compared to the vertical length scale. Therefore, we can take a direct integration of the equation and obtain these two relatively simple partial differential equations that describe the evolution of the velocity and the thickness of ice dynamics. So if we look at these equations closely, it describes the evolution of the velocity and thickness, which are both measurable quantities. However, the viscosity parameter involved in the equations are not measurable at the continental scale. And when we say the effective viscosity, what we mean is really this coefficient between the stress and strain rate tensor. So for Newtonian fluid, this is just a constant, but ice is known as a non-Newtonian fluid. Therefore, we have a non-constant effective viscosity. Usually, people assume that the viscosity is a power law function as a strain rate, but here we do not want to make any assumption. So we know that the knowledge of ice viscosity is critical for the prediction of ice dynamics. And previously, there has been some lab experiment that suggests that the strain rate and stress, the strain rate of ice increase as power law with the stress. So this suggests that viscosity, the effective viscosity, is also a power law function of strain rate. And this laboratory measurement suggests that we will have some power law exponent that's closer to 3. And I will tell you in a few slides that this deviates from what we see from the real data. Okay, so the problem of this simple rheology law is that this was found from the laboratory setting, but the realistic parameter range is quite different from the laboratory. So the strain rate can be as low as 10 to the minus 11, 1 over a second. And this is the range that's very difficult to reproduce in the laboratory. So here we want to find out whether, without assuming the rheology model, can we learn the correct viscosity from real world data? So what we're going to do is we're going to take the data observed from space. We have a velocity and the thickness data that's available in the past 1 decade. And we're going to try to find the viscosity along with the velocity and thickness observation that is consistent with the governing equations. Okay, so for the PINN, we're going to use the neural network to parameterize the viscosity field, the velocity and the thickness. And we'll try to find we'll predict the velocity and thickness that closely agree with the observations. At the same time, we will find the viscosity that, along with the data set, satisfy the governing equations. And I want to point out that in many of the geophysics inverse problem, the first thing we need to be careful about is to make sure the problem is well posed. If the problem is not well posed, then prediction will not be unique, and then you will get bad solutions for it. So here we have to add this stress balance at an ice prompt to make sure the problem is well posed. Okay, so before talking about real data, I want to discuss some of the observations that we saw when we try to solve the problem with synthetic data. So here we try a reduce the problem to a one-dimensional problem. Here we just have the velocity that increase with the along the x coordinate, and we have the synthetic data that include a velocity profile and the thickness profiles. And the short story is that we can use PINN to find the viscosity factor very well. However, there are also some parameters that's very important when that guide us to find the right solution. So here we have we weight the equation and the data loss differently. So we have this gamma parameter that parameterize the importance that between minimizing equation and data loss. Okay, so something we observe is that this is a plot of the prediction error of the viscosity versus the prediction error of the velocity. And for the case when we have clean data, you can play with the importance of these weighting parameter. So for different weighting parameters, we have different prediction errors. In this case, actually, this is what we want because these solutions correspond to the lowest prediction error. For each weighting parameters, we run the experiment for exactly the same setting and exactly the same weighting parameter for 500 times to see the solution distribution. And what we see is that the solution tends to collapse into two different clusters. So this cluster is basically one of the local minimum that's near the true solution, and we don't want the solution to be there. This is the solution that corresponds to what we want. And of course, we can start to inject noise, and then we see you still have these two different clusters, and the desirable solution is in this one cluster. The error is larger simply because now we have noise in the data set. So here we ideally want to find the correct weighting for the equation such that we can minimize the prediction error. And here you can see the best weight we want to find is this correspond to this 10 to the power of 5 weighting ratio. And here we also plot the probability. So looking at each of the 500 trials and characterizing the number of trials that fall into the right solutions. So here is the probability of avoiding local minimum. So this is the probability that the solution fall into this correct cluster. And we see that for clean data, actually the best gamma is this values because that corresponds to almost 100% success to fall into this right cluster that we want. However, for the noisy data, here we know that 10 to the power of 5 ratio of the weighting parameter is what we want. That gives the best prediction error. But at 10 to the power of 5 ratio of the weighting parameter, there's actually a high probability that the solution will fall into the wrong local minimum. So this is just another way. There's a question.
Yeah, if you don't mind, can you? So what's the prediction error of the viscosity? Do you have knowledge of what's the actual viscosity or?
Right. So in this synthetic case, because we know the function, so we can quantify it. But this is why I think it's important to go through this exercise before the real data case. So here it's just another visualization to show that how the desirable, if you do the test systematically, you can see a clear sweet spot for the weighting parameter that correspond to the lowest prediction error that we want. So we tried this for a range of different settings, and what we see is that for deeper neural network and more collocation points, so we have up to 1,000 collocation point and 6 layers, and each layer have 20 units. We still see this kind of cluster behavior, so it persists for a wide range of neural network depth and collocation point. And one of the work in progress is to steer the training by first using we know that there are certain weighting parameters that can avoid the local minimum more easily in the beginning. So we're trying to take a gamma that avoid the local minimum in the beginning of the training. And then after we avoid the local minimum, we switch to the optimal weighting parameter that can guide to the best solution. Okay, so these are some things just to be careful about when we solve this kind of highly nonlinear PDs. And we show that, so from what we learned, we can actually easily extend the approach to a 2-dimensional problem. So now, again, we have the training data of the velocity. Now it's in two-dimensional world. So we have velocity and thickness. So we can use a neural network to, of course, approximate this velocity and thickness field very well. And we can predict the viscosity. So again, the viscosity is predicted by the neural network. We do not include viscosity as a training data to the neural network. However, the neural network can predict the viscosity precisely without the knowledge of viscosity, because this is predicted purely based on the equation itself, and it agrees very well with the ground truth. Okay, so I guess in the last few minutes, I'll just share with some of the findings we got with real satellite observations. So now this is the real data from satellite. We have the velocity and thickness. And again, the neural network can fit this data very well. And by using the PINN to solve the governing equations, we can predict the viscosity field. Again, there's no training data, so this is predicted purely based on the momentum equations. And then we can quantify the prediction error. So here there are orders of magnitude smaller than the magnitude of different terms in the equation. And so now with this viscosity field, we can do many interesting things. You know, we can start to calculate using the constitutive law to calculate the stress using the viscosity. And we can assess the evolution of the flow law, the constitutive law on this ice shelf. So here what we did is we plot the stress and strain rate relationship along one of the flow lines across the entire ice shelf. So we start with some compressive area, and then this flow line passes all the way into the extensional zone. So what we see is, interestingly, in the compressive area, the stress and strain rate exhibit an excellent power law relationship. However, this power law exponent is closer to 1. So as you remember in the laboratory, previously people found that n is 3, but here we see n is actually close to 1. And near the extensional zone, actually we find that power law is just not a good model for viscosity. And we can do this for several other ice shelves, and we consistently find that you can have strain rate and stress that exhibit good power laws. However, the power laws range, and the power exponent ranges from 1.8 to 3, and they're smaller than what's previously thought. Okay, so to summarize, in the compressive area, we find using PINN and our post-processing that the viscosity follows a power law rheology. However, the exponent is between 1 and 3, and this is smaller than the previous experimental result. And when we look at the extensional zone, what we see is that there are usually lots of fractures on ice shelves, and likely this is one of the reasons that give rise to the uncertain rheology that we saw. Okay, so I guess we should probably save time for questions, so I will skip the summary. And I just want to say that we have, I found PINN a powerful tool for both the first the solution discovery problem and the data-driven inverse problem. And it requires a lot of domain knowledge to improve our cost function to help the PINN to find the right thing. And now I'm very excited about trying to develop a deeper understanding to rationalize the PINN result. Okay, so here are some of the link to the paper that I talk about today, and most of the work is done by my postdoc Yangji and my student Yuno. Okay, with that, I'm happy to take questions.
Yeah, thank you, Professor Lai. That's a wonderful talk. Yeah. Do we have any question from the audience? George, do you have any?
I have a question.
Go ahead.
One, that was a phenomenal talk. Have you looked into, as opposed to fitting a power law rheology, have you attempted to develop a data-driven rheology closure that could maybe get both regimes?
Yeah, that's an excellent question. So absolutely, I've seen there are many recent papers about coupling some symbolic regression algorithm with PINNs. So one of the idea is now, instead of doing power laws, that's actually what we're working on right now. So what I'm showing today is some, I guess we wanted to make sure that we are not making too much assumptions about the rheology model. So that's why we were just doing pure fitting ourselves. But now, because we see power law behavior and some other behavior, we have a better understanding of the possible behavior. So now it's an exciting idea to combine with some regression method to fit the best model.
Is your assumption that you have enough of a state to close the problem? Like just with the hydrodynamic variables, is that enough to close the system, or do you need to incorporate some other information? Right, because there's a fracture process that's going on, right? So there's some, you may not just be able to get it with a hydrodynamic closure.
Exactly. That, I think that's the hardest problem right now, is what are the state variables that matters for, especially for the extensional area. So what you were suggesting for, finding a model, I think that will work immediately. That will work well for compressive area, where we kind of understand the state variables that matters. But for the extensional area, indeed, we do not know all the possible parameter state variables that matters. And that's something that I'm very interested in working on right now.
Interesting. Yeah, thank you very much.
Yeah, if you have good papers or good algorithms, I'm very happy to.
Yeah, happy to follow. I'll send an email and follow up offline.
Yeah. I have a question. It's Mauro. Yeah, really nice talk. I have a question regarding the fact that so the viscosity typically depends, as you said, on the strain rate. I mean, that's what you think, and the temperature. How did you factor in the temperature in these estimates that you came up with?
Sorry, Mauro, can you identify yourself?
Yeah, I'm Mauro. I work with CCROX, and I work in particular on ice sheets modeling and initialization.
I've seen your work.
You work at Sandia, yeah.
That's Sandia.
It's very nice to meet you. That's an excellent question. We have actually fit the rheology model. The more complicated version of what I'm doing now actually include the exponential dependence of viscosity on temperature.
Mm-hmm.
So it's interesting because for some regimes we can actually we can fit the composite flow rheology into what new and refined and recover. We capture the temperature effect, and then the only free parameter is the grain size of ice. And we actually can infer the grain size, and the grain size we get is about a few millimeters. So we can essentially, for the compressive part of the regime, we can actually include viscosity effect through the composite rheology.
Mm-hmm. And so I see. So but for the estimate you gave at the end for the Glenn-Low exponent, for retrieving those, were you factoring in the temperature or not in that case?
So in that case, we let the exponent, the prefactor to be, the prefactor here is just a free prefactor, but we can explain the prefactor by temperature and grain size. So maybe I can also follow up with a more detailed plot, because here you can, the temperature influence the prefactor, right? It doesn't influence the exponent.
Yeah, that's what I was interested in, how you factor that in here. I see.
Yeah.
And so,
Great
so
question.
something else that might be interesting, and I think you mentioned that is really to find ways to find where the ice is damaged, and so I don't know if in this simulation I cannot quite see it, but if you were able to like detect like the shear margins, because usually there you see that the viscosity changes significantly. And in some cases, where there are the shear margins, there are some studies that suggest that this n exponent is like larger than 3 because the ice becomes softer. I don't know if you were able to.
Oh, I would love to have actually more time to talk about this together. Can we follow up? Because I have another meeting soon, actually, but I'll write you an email.
Yeah, no, absolutely. Thanks. And yeah, I don't know. I don't know if you have my contact, but otherwise I can send you an email. Okay.
Yeah, sure, absolutely.
Yeah, I think you are saved by the bell, because I see Panos ready to ask a question about the singularity, the first part.
Oh, I'm happy to answer a question too.
Panos, am I right or not?
Yeah, just a quick question. So in the case of burgers, for example, if you take as an initial condition a sine of x, you can compute that there will be exactly the time of the blow up, and that the exponent with which the magnitude of the derivative blows up is exactly what it is. It goes as 1 over t. So have you tried simple examples like that?
You mean, have I tried like Berger's equation?
Right. I mean, not just Berger's. I mean, you tried Berger's equation, but to try to find the lambda and the smooth self-asymptotic, self-similar solution for specific initial conditions where we know exactly how the solution blows up.
Oh, I see. You're saying that.
Yeah, if you take as an initial condition sine of x in the 0 to pi interval, you know that at time 1 a singularity will form, and that the magnitude, the maximum of the magnitude of the first derivative with respect to space blows up as 1 over t, where t is time. So
right.
Have you tried to actually estimate the t0 when the singularity happens and the blow up rate? Because you have an exact, yeah.
This is a very good idea. We will try that.
Just so as a benchmark, it's like, you know, a sanity check, because I see these very nice, smooth, self-similar solutions, but I want to see how well it does for a specific case where we know analytically, and we can compute exactly the exponents and the time of the singularity. Because in your results, I never saw any estimate of the t0, the time of the singularity.
Exactly. Yeah. Because here we are. So you're thinking about basically solving the problem in a space and time domain, right? And you know the time at which you know the t naught analytically. Here we are avoiding that a little bit by we're directly looking at a singularity near the singularity. So the time, our time 0 is the blowout time, and then we're looking slightly away from it. So we already specify what the time of singularity is. But I think it's a very good idea to solve another problem where we actually evolve a solution from some initial sinusoid, like a sinusoidal signal you mentioned. And then
you can put time t0 as an extra unknown, like you have lambda, right? You can have t0 and see if you can get the time t0 that we know analytically for a very specific, let's say, initial condition like sine of x.
Exactly. Yeah. So that is doable.
Yeah, just as like I said, as a sanity check to make sure that, you know, you can reproduce things that we know analytically, for example, for the inviscid burgers.
Panos, can you identify yourself so Yao can follow?
Yeah, I didn't identify myself because you already said so. Yes, so I'm Panos Tinis. I'm from the Pacific Northwest National Lab, and I collaborate with George.
So Yao will follow up with you guys because she has to go, but she will also move to the West Coast, so she will be closer to you guys. She will go to Stanford soon. So
that's right.
Congratulations, Yao.
Thank you, George.
And I think we should let Yao go because she has a meeting. But thank you very much, Yao. Zogren, maybe you can close the proceedings for today.
Okay, thank you.
Thank you.
Yeah, for your talk. And so this is it for this week's Crown Seminar. Everyone has a good weekend. I'll see you next week. Bye.
Thank you. Have a good weekend.
Thank you.